Good evening, guys. Hope you're doing well. We're going to get started with Lecture 6 for Chem 111. This is a bit of a change from the direction that we've been in so far. Everything that we've talked about thus far has to do with equilibrium, using equilibrium constants, acids, and how they play into that. So we use the acids to introduce equilibrium constants. Now we're going to move into something that's a bit different than that. We're going to be talking about oxidation reduction reactions, which we call redox. I'll explain why they're listed as redox reactions and not oxidation reduction reactions. We'll talk about some of the basics of how those equations work. We'll get through balancing those equations in this lecture. And then in the next couple lectures, we're going to be looking at applications of redox reactions and what we use them for, how that happens. Okay, so I'm going to go ahead and share my screen. That way you guys can see what I'm looking at, because that makes more sense. So again, lecture 6, which contains information from section 4. That's where your textbook introduces redox reactions. That's pages 137 to 141. And the activity series, which is something we talk about on page 143. We then go into chapter 18, and we're only covering section 1. Redox reactions using the activity series and balancing redox reactions. So let's talk about those details. And of course, if there are questions, comments, problems, any of that, you know how to get a hold of me. Email, phone calls, whatever. If you are feeling a need to come and talk to me and you haven't done so, I've set up some WebEx with people recently. I've had people come to my office. Please get a hold of me if you're having issues with what's going on in the class. Okay? So redox reactions. So we take a reaction. We've looked at something like this before. 2CaS plus O2 gas goes to 2CaO. And we know that CaO, being a metal and a nonmetal, that's an ionic compound. And so Ca becomes 2 plus, O is 2 minus. That's a neutral compound. Yay. Well, how did Ca become Ca2 plus? How did O go from O2 to 1O2 minus? How does that happen? Well, that's the process that we're going to be talking about. So calcium solid is oxidized. It loses electrons. So CaS, or Ca solid, goes to Ca2 plus 2 electrons. In the case of the oxygen, we go from O2 to 2O2 negative. And of course, that means a transfer of electrons. So those 2 electrons that came off of the calcium are actually picked up by one of the oxygens. And of course, to balance that, we have to have 2 of the calciums for the O2 that we have. That means that we've lost electrons from the calcium, gained them in the oxygen. We call one of those processes oxidation. So lose electrons, oxidize. And the other one is called reduction. So gain electrons, reduce. And it's reduction because we've lowered the charge because we added an electron. Okay. So they have to occur together. We cannot have a bunch of a material spitting out electrons that go absolutely nowhere. So they have to come together. And that's why we call them redox. Not only do they have to happen together, but the same number of electrons that are lost must be picked up. Okay, so that's the process that we're talking about there. We'll get into more of the terms and some other terminology that goes with this a little bit later on. One of the things that we talk about are oxidation numbers. This is also known as oxidation states. So we have Zn solid, which then reacts with 2HCl to become ZnCl2 plus H2. Now, if we think about this in the 110 sense, that's all we have to care about. But we know now that Zn solid is a bunch of Zn atoms that are bound together. And HCl, we actually have 2 H's, which are the H+, these are the positive guys. And we have 2 Cl-, which are these negative guys. Sorry, I'm trying to get some annotation. Oh, and that was the other thing. I am going to be doing some annotation on the slides today. It's not going to be very legible. What I will do after the fact is I have an electronic paper that I've been able to show on my personal computer that I can't show on this computer. So I will walk through some of what I did there. And since my camera won't show it, I will upload that paperwork for you so you can take a look at it. Okay. Anyway, so we have our Zn solid atoms. They react with the 2H plus and 2Cl minus. That gives us Zn2 plus and 2Cl minus, which are still just sitting there just like they were before. So those are our spectator ions. And we get H2 gas. So if we were to talk about this from a net ionic equation, we have Zn solid plus 2H plus goes to Zn2 plus H2. And again, we do that net ionic because we don't care about the fact that the chlorine's there. The only reason it's there is to balance charge. It doesn't matter if it's chlorine or nitrate or anything else. It could be anything. It's only there to balance charge. And while we know that it's necessary to have it, it's not necessary to the reaction that we're doing. So it's not important that it be part of that net equation. Okay. So oxidation numbers help us keep track of what loses electrons and what gains electrons. So this is the description of oxidation numbers. Now, like I said, I was going to do some annotation. I'm going to pull my pen, and we're going to talk about hydrogen, because for me, hydrogen is the more fun one. So we have an H plus, right? It starts as an H plus. And I have 2 of those. And I add 2 electrons. And that gives me H2. Now I could have done this in the more traditional. H plus goes to H2, and then I need 2 H's, and then because this is 2H plus, or 2 plus, then I need 2 minus. Oh, and that's 2E minus, sorry. Didn't write everything. What we have in this case, this hydrogen that's here is a positive charge, right? We know that he's a positive charge, and he's happy. His oxidation state, we will talk about what its value is right here, but it goes from positive to 0. So since it goes from positive to 0, the oxidation number has decreased. Since it's decreased, then that element is reduced. So this is the one that gain electrons reduce. We'll get to that. We'll tie all of this together in just a minute. But that's what we're doing here. Okay, so that's what we're talking about, is the change in oxidation number. All right, and I'll show you what those values are in their native state, so then we can talk about how we see how they've changed. So let's talk about how they exist in their native states. So a couple of rules that we need to know about. The sum of the oxidation numbers in a neutral compound is 0. All right, so if I have H2O, then all of my oxidation numbers have to be 0. The sum of the oxidation numbers in a polyatomic ion is the charge on that ion. So if we have PO4 3 minus, the sum of the oxidation numbers has to be 3 minus. Elements in their elemental form have an oxidation number of 0. So for those 7 gases that occur as diatoms, so hydrogen, fluorine, chlorine, bromine, iodine, nitrogen, oxygen, those guys, they're like the O2, H2, Br2, Cl2, I2, N2, those states, that oxidation number is 0. Okay. The oxidation number of a monoatomic ion, so single atom ion, is the same as its charge. So for an H plus, its oxidation number is plus. Okay. Oxygen has an oxidation number of -2, except in the peroxide ion, in which it has an oxidation number of -1. Okay. Hydrogen is -1 when it's bound to a metal, +1 when bound to a nonmetal. So if I have hydrogen bound to chlorine, which is a nonmetal, he's going to have a +1 charge, and the Cl is going to be -1. In the case where he's bound to a metal like hydrogen, NaH, the Na is plus, and the H is -1. Okay. Fluorine is always an oxidation number of -1. Other halogens have an oxidation of -1 when they're negative. Okay, so if they're a negative ion, they're going to be negative. But there are times when halogens occur bound to oxygens, so in oxyanions, where they're going to have a positive charge. That happens. So oxygen is always going to be -2. That halogen may have to change because it's bound to oxygen. The oxidation numbers can be fractions as well as integer values. Okay, so there is the ability for us to have a fractional oxidation number. That's something we need to be able to deal with. Okay, just like we did that when we were talking about balancing equations, we can have the same thing here. All right. Sorry. So the synopsis of what I just talked about: elements equal 0. Monoatomic ion equals their charge. And then elements includes how they exist in nature. So an element such as hydrogen that's diatomic, that goes there. Monatomic ions equal their charge. Fluorine is -1. Oxygen is -2 unless it's in peroxide, and then it's -1. Hydrogen is +1 unless it's on a metal hydride, and then it's -1. The sum of the oxidation numbers equals the overall charge, and in a neutral compound, that's going to be 0. So that's a synopsis of our rules. Let's do some practice predicting oxidation numbers. Okay. So if I'm going to predict oxidation numbers, I need to look at what this list is that I have. I have an O2. O2 exists as O2 in nature. So O2 in its elemental state, that oxidation number is going to be 0. When we talk about H2O2, we have our hydrogen, which is bound to a non-metal. So the oxidation number of each hydrogen in there is +1. In the case of peroxide, we know that oxygen has an oxidation number of -1. So we see that. When we look at NaF, we know that F is always an oxidation number of -1. If F is -1, Na has to be positive anyway because he's in that alkali metal group. So he's always +1. So that makes sense. And his oxidation number equals his charge. We can talk about the H3PO4. So 2 things to consider. 1, we have a polyatomic ion, PO4 3-, right? The H+ is bound to that, and that's a non-metal bond. So the H+, each one of them is a +1 oxidation number. When we talk about the PO4 3-, we need to consider what we have in that polyatomic ion, right? So let me show you, let me find some pen, not that, this. So let's talk about P, if it'll let me draw. P, the O, and of course, there's 4 of those, and then our overall charge for this thing is going to be 3 negative, right? Or -3. So I know that oxygen is -2. I know that I have 4 of them. And that gives me a total of -8, right? So I know that if this is -8 and I need to have an overall charge of -3, then since there's only 1 phosphorus, whatever that charge is has to give me, so I add this value to the -8 and get -3. In order to do that, this must be +5. And that's what we would have right there. So phosphorus is +5, oxygen is -2, H is +1. Okay? So that's that guy right there. Let's talk about our Fe and then our Cr and O. And we're going to talk about these a little bit separately. So we did have a funky looking line. Let's talk about our Cr and our O first. So Cr2O7, there are 3 of them. I happen to know from looking at the polyatomic ions that Cr2O7 is 2-, right? So my overall for this last part is going to be -2. I know that in oxygen, it's always -2, and I have 7, which gives me a total charge of -14. Okay. Now, when we consider just this ion on its own, -2 is my result. I have -14 there. That means I need to have a +12 here to make that math work, right? But I also know that I have 2 of those chromiums. And that means that each one of them is going to be a plus 6. And I write that over my funky line. So each one of them is going to be a plus 6. So my oxygen is a minus 2. My chromium is plus 6. Now we deal with the iron. So I know that I have iron. I know that since Cr2O7 is 2 minus, that's how I get this 2 on the Fe, then the Fe has to have a plus 3 charge. So he has to be plus 3. That's the only way that can work. And that's how we do the cross multiplication. So since Cr2O7 is a 2 minus, I have a 2 here, that means that in order for that negative 6 to be equal, because that's what that gives me. With this negative 2 times 3, that gives me a negative 6. And I know that with the 3 irons, I have to end up with a positive 6 to make that a neutral compound. Since there are 3 of the irons, then, 2 of the irons, oh my lord. 2 of the irons, and each one has to be plus 3. Okay, that's how I got to that. So hopefully I didn't just confuse the hell out of you. Sorry if I did. All right, let's talk about the next one. So Hg2 Cl2. Now I know that Cl is going to be negative 1 unless it's bound to an oxygen in weirdness, an oxoanion. So my Cl is going to be negative 1. I have 2 of them. It gives me a total of negative 2 for the charge there. This is a neutral atom, so this has to be 0 for the overall. My Hg, I have 2 of those as well. And that has to equal positive 2. And so that means that the charge on each of those must be plus 1. Okay, so in that particular case, we have an Hg2 plus Cl. Each individual one in that case is plus 1. But since it's an Hg2, what we're actually looking at, the ion that you'll see, Hg2, 2 plus. And that's how we end up with the 2 chlorines. But each individual Hg is plus 1. Okay? When we talk instead about Hg Cl2, so we still have the same information for our chlorine. Cl, we're going to have a negative 1 on that. There are 2 of them. We know this is neutral. And that means that this Hg, in order to make that happen, has to be plus 2 overall. There's only 1 of them. And so to make that work, this charge must be plus 2. Sorry for my unclear hand scratching, which is why I'm giving you better notes. So that's what we're talking about there. So that Hg is a plus 2. All right, I'm going to erase some of these annotations, at least I hope I am, so that we can find some more space. And like I said, I will make these notes available to you similar to what I've shown before. Now I have them handwritten on this lovely little electronic paper that I have. I will make those available to you. I can PDF those and put them up. That's not a big deal. It's going to bug me if I don't get rid of it. I'm sorry. I might have a little OCD. Okay. So having done that, let's get our pen back. And when we talk about NaH, so we said that H has a plus 1 oxidation number unless it's bound to a metal. Na is a metal. So I know that Na, being an alkali metal, it has a plus 1 charge. That means that H has to be a negative 1 charge. Okay. If I want to look at BaO2, now Ba typically we would expect it to have a 2 plus charge. But I can look at this molecule and I can say that can't be the case. Because in order for there to be 2 of the oxygens, if each one of them is -2, which it certainly is, then that negative charge is 4. Since this is a neutral compound, I have to have my 1 Ba be the entire source of that charge, and so he has to be +4. Okay, so that's the oxidation number for Ba is +4, and the oxygen is -2. We have one more to talk about, and that's this MoO3. Really ugly. Wow. So we'll look at our molybdenum, MO. We'll look at the oxygen. There are 3 oxygens that have a -2 oxidation number. That gives me a -6. I hate doing this with a mouse. This whole thing has to be a 0. I have my MO there. In order for that to happen, that has to be a +6, because otherwise I don't get a 0. And since there's only one MO, it has to be the source of the entire set of charge. So my oxidation there is +6, and my oxidation number for the oxygen is -2. Okay? So that's how predicting oxidation numbers work. Will you need to do that? Maybe. You might get asked a question like, predict the oxidation numbers for these. That's a possibility. One of the other things that you might see is that during the balancing of some chemical equation, you might get asked, oh, out of this stuff that you're looking at here, what is the oxidation number on this species? What are the oxidation numbers for all of these things? You know, some combination of those things. I'll show you an example of that as we go on. But that's the kind of thing that we're talking about. So that's where I would expect to see that moving forward for you guys. Okay. Oxidation numbers are simply a way for us to keep track of who had how many electrons where. So that helps us determine who lost electrons, who gained electrons. Okay. So we talked about this a little bit before. We said a species is oxidized when it loses electrons. So zinc solid goes from an oxidation number of 0, because it's a solid, to Zn2+. Since it's a monatomic ion, its oxidation number is +2. Since its oxidation number has become more positive, that means he has lost electrons. Lose electrons, oxidize. And again, lose electrons, oxidize. Let me show you a little bit. So we say LeO, and sorry, wrote the wrong thing. I hate it when I do that. LeO and then GER. Now there are other mnemonics for the same thing, and I'll share with you the ones that I know. This is the one that I remember, and it's the one you'll hear me spouting when I'm trying to think. So a species is oxidized when it loses electrons. A species is reduced when it gains electrons. So lose electrons oxidized is LeO. Gain electrons reduced is GER. And one of the things that we say is Leo the lion goes GER. So we remember lose electrons oxidized, gain electrons reduced. The other thing that I've heard is oil rig. Oxidation is loss, reduction is gain. So helping to remember, if I'm gaining electrons, that is my reduction, yada, yada, yada. Okay, so that's what we're talking about there. Now, one other thing that we need to talk about, and this is the part that always throws me for a loop. An oxidizing agent causes something else to be oxidized. So if I look at this, I see that 2H plus, which is a +1 oxidation number, goes to H2, which is a 0 oxidation number, right? So my oxidation number for H2 has gone down. That means I gained electrons. When I gain electrons, I am reduced, right? So H plus gains an electron, forming H2. Well, two. An oxidizing agent causing something else to be oxidized. Okay, so my oxidizing agent is H plus. It causes the oxidation of zinc. The reducing agent causing something else to be reduced. So since H plus is reduced, the oxidizing agent is the zinc. Okay, so you'll probably hear me saying this. Okay, I have this here, my electrons are here. I'll go Leo goes Gur, figure out which one it is, and then I'll go, okay, because this is this, then it's either an oxidizing agent or a reducing agent because it caused this and something else. I know that that's a really long and circuitous way to get from point A to point B, but that's the way it works in my head. And there are some things that we'll talk about in the next lecture that, for me, solidify that. And so while I understand that people may want me to go faster, that is not something I am capable of doing. I have to go step by step to get from where I started to where I end, because that's how I am. I'm methodical and stepwise. So I apologize if I'm irritating you by doing it in that way. All right? So now we've talked about oxidation. Species is oxidized when it loses electrons. Species is reduced when it gains electrons. Leo the lion goes grr, lose electrons oxidized, gain electrons reduced. Oil rig, oil is lost. Rig, reduction is gain. An oxidizing agent causes something else to be oxidized. So it is the thing that is reduced. And reducing agent causing something else to be reduced. So it is itself oxidized. Okay? So that's how we define redox. Now we can talk about an activity series. So when we have an activity series, you'll see that we have a bunch of reactions where we are looking at reductions. So we lose electrons. They're all set up as reductions. So the way that this is ordered is that the reducing strength increases as we go up. What that means is that anything that's higher on the table has a greater desire to lose electrons. So Li plus has a greater desire to lose electrons than potassium does. Sorry. Lithium has a greater desire to lose electrons than potassium does, not Li plus. So anything that's above in this table, if we're looking at reduction, is going to be a better reducing agent. Okay. So if it's below, that means it's a better oxidizing agent. This table can be used to make predictions about who's going to react with what. I'm not overly great at doing that because this is not how I think about it. So I may struggle if you ask me to predict based on this table. I will probably want additional information. And unless I'm looking right at this, it's going to be hard for me to do that prediction. I found a way that worked for me, and I'm having, for some reason, it's harder for me to figure out how to explain to somebody else this. And I know why. It's because my mind doesn't think that way. But I haven't figured out how to get around that. And it kind of trips me up because a lot of things I have been able to figure that out. Okay? But that's our activity series. So you may get a table like this on the test. It's not in the, actually, I don't remember if it's in the handouts. Let me see if it is. Hold on. Bear with me, I'm pulling up. Same handouts. Is this the right one? I don't think that this is in the overall handouts. No, it's not. But you may see this image and be asked about it on a test. Okay, so you may see an image, either this one or one like it, and be asked about it on the test. Okay. Now, let's talk about one other thing. So the way that we do balancing for these things is by what we call the half reaction method. So we take this oxidation and this reduction. So we have one thing where a species loses electrons and one species that gains electrons. And so we have effectively two reactions that are going on, where we have an oxidation. This SN2 plus goes to SN4 plus, giving off 2 electrons. And then the following reduction, where 2 Fe3 plus those 2 electrons goes to 2 Fe2 plus, right? So we know that those are two separate processes, and we can, link them together, talk about their combined Ks. There's some other numerical values that we're going to be talking about soon that we can do with that. But when we do our balancing, this is the way we're going to do it. So we write an oxidation one, we write a reduction one, and then that's what we use to do this, okay? So that's the beginning of this. So I have an oxidation reaction and a reduction reaction. Then I want to balance those redox equations. This is the half reaction method. This is a synopsis of how it works. I'll walk you through the synopsis, then I'll show you an example. So we're going to make two half reactions, similar to what we just saw, the tin and the iron. We're going to balance the atoms other than oxygen and hydrogen. So in the example that we just looked at, we'd be looking at tin and iron, right? Once we've dealt with the tin and the iron, then we're going to have to deal with the oxygen. We deal with the oxygen by adding H2O, okay? So we balance the O there. Then we balance the H by adding H+. Now we have this lovely combination of things that is probably not going to be electrically neutral. So we're going to add electrons to both of those half reactions to balance the charge. The next thing we need to do is make sure that we have the same number of electrons in both half reactions, and then we add them together, all right? So if we need to multiply things to make the number of electrons the same, we need to multiply everything, not just the electrons, and then we add those two. We can simplify them by dividing by a common factor or converting H+ to OH- if basic, and we'll talk about that too. And then you want to double check everything, make sure that you're good. So that's the basic process that I'm going to be working through when I do all of this balancing. We're going to do one example in detail. Let's talk about that one. So we want to consider a reaction between MnO4- and C2O42-. Yeah, right. Oh, how do we do that? Grab my paper again. I apologize. Paper's sleeping. So we have MnO4- plus C2O42- goes to Mn2 plus CO2. All right. We have two half reactions that we're going to get out of this. And we're going to do those. So what are the two half reactions that we're going to deal with? Now, I know that I'm skipping the assigning oxidation numbers because I don't do that first. I write my half reactions first. So my first half reaction, and I'm not actually going to write this because the paper I'm going to give you has it, but and it's complicated to do this way. My first half reaction is the MnO4- going to the Mn2 plus. Our second half reaction is the C2O42- going to CO2. Okay, so those are my two half reactions. I would then write those as two separate equations, and I'll show you that right here. C2O42-, and I've left off the states at this point. I would need to include them at the end if I was going to do anything else with them, but I'm not going to include them here because in the balancing and the redox, the states are not important. So C2O42- goes to CO2. We then have our half reaction for our MnO4, and I'm going to write these here. going to Mn. And I'm going to show you on this slide a condensed version of what you're going to see on the paper. Okay, so if you're looking at this lecture, please go print that paperwork out so that you can see exactly what I've done on that paper. I'm going to show you a condensed version of it here. So write down our two half reactions. And again, I will come back to the oxidation numbers and what is oxidized and what is reduced. So I write down my two half reactions. These are my two half reactions. I want to know, are the number of MNs the same on both sides? Yes, I have one MN and one MN. However, I am not good with carbon. So in that case, I have C2 on the reactant side, CO2 on the product side. So I'd have to do that so that I have two C's on both sides. Now, I'm not concerned about the oxygen yet. Haven't gotten to that. Let's talk about how we do that. So how many oxygens do you have on the reactant side in your C2O4? I have 4. Okay, how many do I have on my product side? I have 4. So that one's happy. That guy is happy with his oxygens. Let's talk about our MnO4. So MnO4 here goes to Mn2+. I don't have enough oxygen. So I'm going to add oxygen to that. And you'll notice that I do not do it like this when I write things on paper, because I get tripped up if I do this. Inevitably, I make a mistake and I cannot deconvolute everything that I've written down to figure out where I made it. So if I write everything stepwise and I have each equation as one single step as I do this. So I write my half reaction, C2O4 minus goes to CO2. And then I do the next line and it's balancing the C's. So it's C2O4 minus goes to 2 CO2. And then I have a line for my oxygen and I write okay, because I know it's fine. Either that or I draw a line to indicate that it was the one before it. Sometimes I'll actually even write it out again. It depends on how lazy I'm being. But that works better for me. Okay. So now I've dealt with my oxygens. But now I don't have balance for hydrogens. So I have 8 hydrogens on my product side in my MnO4 minus thing. So I add 8H plus over here. And of course, if I look at my other half reaction, the one for the C2O4 2 minus, then I don't have balance there either. So I have the same number. Actually, I have that one's fine. My oxygens are fine. I have no protons. I apologize. Now we want to look at the charge. So if I look at C2O4 2 minus going to 2CO2, the net charge on the reactant side is 2 minus. The net charge on the product side is 0. So I need to add 2 electrons, 2E minus, to my product side to make both sides be 2 minus. Okay. Same kind of thing is going to happen when we look at the other half reaction. So again, I have a total of 2 plus on the product side. I have a total of 7 plus currently on the reactant side. And so if I want to add electrons to make that happen, then I need to add 5 electrons to do that. Sorry, I was looking at my hand scratching. It made no sense to me. So I'm going to take and do 5. Ooh, slightly different color. Sorry. And add that there. And that's going to give me a net of 2 plus. So 5 minus, or 8 minus 5 is 3. Minus 1 more is 2 plus. So I'm 2 plus on both sides. Now, notice I have 5 electrons in this half reaction for the manganese, and I have 2 in my C2O4. Now, I'm going to change colors a little bit, but what I need to do is make those numbers the same. So lowest common denominator between 2 and 5, 10. So I multiply this reaction by 5. And then I take and I multiply my other half reaction by 2. I'm going to throw the 2 out here. And this is when it starts to get really messy. So I know that I'm looking at that going, what the hell? So for me, I cannot move any further forward from there. What I have at this point, and I'll write it up here, I have 10 E minus plus 16 H plus 2 M N O 4 minus goes to M N 2 plus. Oh, see, there aren't enough of them. I need 2 of those because I'm going to multiply everything by 2 plus 8 H2O. All right, that's one. Go half of the 1/2 reaction is satisfied. Let's take a look at our other one. So 5 times the C2 gives me 5 C2O4 2 minus. That then goes over and gives me 10 CO2 plus 10 electrons. The next thing we're supposed to do is simplify and add. Well, okay, if I'm going to simplify, I have 10 electrons there, and I have 10 electrons there. So when I do this addition, I'm looking for anything that's common. Now, those electrons have to disappear. If they don't disappear, I have screwed this up and I need to start figuring out where. As long as they disappear, everything else gets cleaned from there. So if I were to add this at this point, and I can write this down here, if I can find my pointer. So I'm left with 16 H plus 5 C2O 2 minus going to give me. No, I'm not done yet. Sorry, need to erase. I forgot to add my MN2MnO4. That will go over here. And that will give me 10 CO2 plus 2 Mn2 plus plus 8 H2O. And now you should pat yourself on the back because you have successfully completed balancing a redox reaction. It is a big stepwise process. It takes forever. And if you take shortcuts, the likelihood that you're going to mess up is higher. Okay? But do it how you want to do it. Now, this last reaction that we just wrote, this 16H plus, where's my mouse? 16H plus 5C2O4 2 minus plus 2 MnO4 minus goes to 10 CO2 plus 2 Mn2 plus 8 H2O. This is an acidic solution. This H plus indicates that this is acidic solution. If I am in a basic solution rather than an acidic one, this cannot be the balancing that I have. And the way that we deal with that is to write 16OH minus plus that. And then on this side, we have to add the same numbers, 16 OH minus. Now that I've added both of those, these two add together and I get 16 waters. So 16 waters. I'm going to cross out the waters. And I have 8 waters over here. So I'm going to cross out that 8 and leave this as 8 H2O. And that gets added to the 5C2O42 minus plus 2MnO4 minus, that going to 10CO2 plus 2Mn2 plus 16OH minus. And now I have successfully balanced in both acid and then in base. That is the process that we go through when we do this. Questions, comments, problems. And that's my next slide. Questions, comments, problems. I hope not. Now, the next thing that I have here is the example. And what I'm going to do is hope that you have printed out my notes that I wrote, and I will walk you through those notes as I look at them. So if you don't want to listen to the examples, that's fine. There's one other slide that I want to talk about, and that is our key takeaways. So you may notice as you go through this practice, and hopefully you will practice enough to notice this, each half reaction is completely independent of the other. So if I have a half reaction that I have balanced once, I can use the exact same balancing in another problem. Tables of balanced half reactions do exist, and you can look them up in that half reaction table, and then you can skip all of the making sure that you've added the oxygens and the hydrogens and the electrons, because everything is balanced up until that point. All right. When you do that and you take 2 of those half reactions, when you go to add them together, you still need to make sure that the number of electrons is the same in both equations, and then add everything together and simplify, and then change it to OH minus if you're in basic solution. So those are our key takeaways from that. So like I said, if you don't want to hear me walk through this, how we do all of this balancing, that's fine. I am going to go ahead and walk through that balancing that I have written down on that paper that I'm going to post to D2L so that people can hear me talk about it in the event that they're not clear on what it is that I did. Okay? Well, awesome. I will talk to you guys later. Hopefully that will be soon. And I hope you guys have a great day. For those of you who are staying, let's go back here. So the first thing I'm going to talk about is Pb reacts with the MnO4 to minus to produce the Pb ion and the Mn ion. Balance the equation using the half reaction method and, unless otherwise stated, in acidic solution. So that statement, use the half reaction method and otherwise stated in acidic solution, is supposed to apply to everything. So that's what we're talking about there. And I will... Hold on. Okay. And I do have a detailed written out explanation of the one that I just did that will be posted as well. So we have our 2 half reactions. Pb goes to Pb2 plus, and MnO4 minus goes to Mn2 plus. That's what we mean by the 2 ions. Okay. If I balance for Pb and for Mn, they're both fine. I don't need to make any changes there. When I balance for oxygen, I need to take the MnO4 minus, going to Mn2 plus, and add 4H2O as a product. Then, when I balance for hydrogen, I need to add 8H plus to the reactant side. So I have 8H plus MnO4 minus plus goes to Mn2 plus 4H2O. And of course, the Pb is still fine. I need to look at how many electrons we have. So Pb goes to Pb2 plus needs 2 electrons added to the reactant side. If I look at the 8H plus MnO4 minus goes to Mn2 plus 4H2O, I have 7 plus on the reactant side and 2 plus on the product side. So I add 5 electrons to the reactant side. One other thing that you should note at this point is that the number of electrons, you need to have electrons lost somewhere and gained somewhere. You can't have this work if both of them lose electrons or both of them gain electrons. And I'll add that to the key takeaways. And actually, I'm going to do that right now. So bear with me just a moment. Where did it go? Oh, sorry. Let's have an oxidation and a reduction to make the balancing work. One must gain electrons and one must lose. So I will get that. Well, you'll already have it by the time I do this. So there you go. Sorry. So having said that, we'll go back and slideshow from this point. And so well, I was at the point where I added 5 electrons to my reactant side. So I now have Pb goes to Pb2 plus 2 electrons, and H plus MnO4 minus plus 5 electrons goes to Mn2 plus 4 H2O. I need to make the number of electrons equal, so I multiply the Pb by 5 and the Mn by 2. That gives me 5 Pb going to 5 Pb2 plus 10 electrons, and 16 8, and I multiply the MnO4 by 2, and that gives me 16 H plus 2 MnO4 minus plus 10 electrons goes to 2 Mn2 plus 8 H2O. I cancel my electrons when I add and simplify, so they cancel, and that leaves me with 5 Pb plus 16 H plus 2 MnO4 minus goes to 5 Pb2 plus 2 Mn2 plus 8 H2O. Okay, so that's our first one. Go, awesome. And like I said, you will see all of this hen scratching, and I could try to. I have. How do I get it to show up? I have hen scratching, which you cannot read, but that's what I'm going to make available to you, and that's what I'm referring to right now. Okay, so I have I minus plus OCl minus goes to I2 plus Cl minus plus H2O in basic solution. Okay, so I minus plus OCl minus plus goes to I2 plus Cl minus plus H2O. My half reactions, I minus goes to I2, and OCl minus goes to Cl minus plus H2O. I need to make sure that my I's and my Cl's are fine. The Cl is fine, but the I is not. So I need 2 I minus going to I2. When we then do the water, so balancing for oxygen with water, I need OCl minus going to Cl minus plus H2O. Oh, shocking, that was already there. And then when I do the hydrogens, I only need to worry about that half reaction. So 2H plus OCl minus goes to Cl minus plus H2O. I then need to look at my charge. So 2I minus going to I2, I need to add 2 electrons to the reactant side to make that work. My 2H plus OCl minus goes to Cl minus plus H2O. I need to add 2, I think I said that wrong. I'm sorry. 2I minus goes to I2 plus 2 electrons, which is the product side. I think I said that wrong. I'm sorry. On the other one, it's 2H plus OCl minus plus 2 electrons goes to Cl minus plus H2O. If I make the number of electrons the same, oh, shocking, that's already done because they're both 2 electron processes. So I'm going to add and simplify. I get 2I minus plus 2H plus OCl minus goes to I2 plus Cl minus plus H2O. Now, since that's an acidic solution, and I'm supposed to do this in basic solution, I need to add 2 OH minus to both sides because I have 2H plus in that balanced reaction. If I add the 2 OH minus to the reactant side, I then combine it with the 2H plus to give me 2 H2Os. If I add the 2 OH minus to the product side, I can then cancel the 1 water that's on the product side. And that leaves me 1 water on the reactant side and 2 OH minus on the product side, which leaves me with an overall of H2O plus 2I minus plus OCl minus goes to I2 plus Cl minus plus 2H2O. And that is my basic solution balancing of this equation. And breathe. Let's take a tiny throat. Okay. Al plus ClO4 minus goes to Cl plus Al3 plus. So we have two half reactions. Al goes to Al3 plus, and ClO4 minus goes to Cl. Both of those are balanced for Al and Cl. So we go to our next step, which is to add oxygen using water. The Al equation has no oxygen in it, so we take our ClO4 minus, going to Cl minus, and add 4H2O to the product side. Again, we're going to balance for hydrogen using H plus. The Al equation is fine, so we add 8H plus ClO4 minus goes to Cl minus plus 4H2O. And now we've dealt with that. Okay. Next thing we do is charge. So when we balance for charge, we have Al goes to Al3 plus. I add 3 electrons. So Al goes to Al3 plus 3 electrons. In our other half reaction, we have 8H plus ClO4 minus goes to Cl plus 4H2O. So we have a net -1 on the product side, and we have a net +7 on the reactant side. In order to make them equal, I have to add 8 electrons. So that gives me 8H plus 8E minus goes to ClO4 minus. Sorry, I apologize. Let me back up just a moment. 8H plus 8E minus plus ClO4 minus goes to Cl minus plus 4H2O. So that's that one. In order to make the electrons the same, I need to multiply the aluminum by 8 and the Cl by 3. That gives me 8Al goes to 8Al3 plus 24 electrons. And that gives me 24H plus 24E minus plus 3 ClO4 minus goes to 3 Cl minus plus 12 H2O. We then add and simplify. It gives me 8Al plus 24H plus 3 ClO4 minus goes to 8Al3 plus 3 Cl minus plus 12 H2O. I'm just taking a look at that to see. H of 3 is 24, 3, 3. Yep. I was checking my charges just to make sure they were fine. And they are. So that's that particular reaction. Okay. Only 4 more. So we're going to talk now about Zn plus BrO3 minus going to Br minus plus Zn2 plus. We have two half reactions. Zn plus goes to Zn2 plus, and BrO3 minus goes to Br. In my Zn, I don't need to worry about that until we get to the electrons. But BrO3 minus going to Br needs to be balanced for oxygen. Everything is okay with the zinc and the bromine. So when I balance the oxygen, I get BrO3 minus goes to Br plus 3H2O. I then have to add protons to the other side to balance that. So that gives me 6H plus BrO3 minus goes to Br plus 3H2O. I then have to look and see what the charges are. So Zn goes to Zn2 plus 2 electrons. We have 6H plus BrO3 minus plus 5 electrons goes to Br plus 3H2O. So I need to make sure that I have 6H plus or 6 plus and 6 minus on the reactant side of that BrO3 minus expression, because the other side is neutral. That's why I add the 5 electrons. I then multiply the Zn by 5 and the Br by 2. So I get 5 Zn goes to 5 Zn plus 10 electrons. And I get 10 electrons plus 12 12H plus 2 BrO3 minus goes to 2 Br plus 6 H2O. I add and simplify, and of course my electrons cancel, so I get 5 Zn plus 12H plus plus 2BrO3 minus goes to 5ZN2 plus 2Br plus 6H2O. Yay! Bye! Only a couple more. Solid copper reacts with MnO4 minus and acid to produce MnO2 and water. So 2 half reactions. Cu goes to Cu2 plus, and then MnO4 goes to MnO2 plus H2O. So Cu2 plus is fine for Cu, Mn is fine for the Mn part. We are not balanced for oxygen on the Mn reaction, so we get MnO4 minus goes to MnO2 plus 2H2O. We are balanced for hydrogen in the copper reaction, but not in the manganese reaction. So we have 4H plus MnO4 minus goes to MnO2 plus 2H2O, 4 protons or 4 hydrogens on both sides. We then have Cu goes to Cu2 plus 2 electrons. And we have everything on the product side in the Mn reaction is neutral, but currently we have 4H plus and 1 MnO4 minus for a total of 3 plus on that side. So we get 3E minus plus 4H plus MnO4 minus goes to MnO2 plus 2H2O. We then multiply the copper by 3 and the manganese by 2. So 3Cu goes to 3Cu2 plus 6 electrons. We have 6 electrons plus 8 H2O plus 2 MnO4 minus goes to 2 MnO2 plus 4 H2O. Add and simplify, our electrons cancel. 3Cu plus 8H plus 2 MnO4 minus goes to 3Cu2 plus 2 MnO2 plus 4 H2O. Now, since we've talked about the key takeaways already, you'll see that the balancing on this one for the MnO4 to MnO2 is exactly the same as what we did before. And that's why I mentioned to you guys that you can use that same half reaction again if you know you've already balanced it, or if you have a reference that hasn't, okay? So that's where that comes from. Now, I am not going to give you one of those tables because I expect you to balance your own half reactions, but they can be used that way, right? So now let's talk about CrOH3 plus Br2 going to CrOH4 2 minus plus Br minus in basic solution. 2 half reactions. CrOH3 goes to CrO4 2 minus, and then Br2 goes to Br minus. We fix the number of Brs, so we have Br2 going to 2 Br minus. We fix our oxygens. So CrOH3 plus H2O goes to CrO4 2 minus. The bromine is fine. The hydrogens, we now need to do the chromium reaction, but not the bromine. So CrOH3 plus H2O goes to CrO4 2 minus plus 5H plus. Because we have 3 from the OH group and 2 from the water, so that's a total of 5 that we need to add on the other side. If we look at our charge, CrOH3 plus H2O goes to CrO4 2 minus plus 5H plus, and of course that gives me a total of 3 plus, which then means I need to add 3 electrons to that. We have Br2 going to 2 Br minus, and in order to make that happen, I need to add 2 electrons to the reactant side, so Br2 plus 2 electrons goes to 2 Br minus. Since there are 2 electrons in the Br and 3 in the chromium, we have to cross multiply. That gives me 2 CrOH3 plus 2 H2O goes to 2 CrO4 2 minus plus 10H plus 6 electrons. We then have the 3 times the bromine, 3 Br2 plus 6 electrons goes to 6 Br minus. We add and simplify. That means we cancel our 6 electrons, and we get 2 CrOH3 plus 2 H2O plus 3 Br2 goes to 2 CrO4 2 minus plus 10H plus 6 Br minus, and that's our happiness there. Now, Does it stay there? No, because I have to balance this in basic solutions. So since I have 10H plus, I need to add 10OH minus to both sides. That gives me 2CrOH3 plus 2H2O plus 3Br2 plus 10OH minus. And then 2CrO42 minus plus 10H plus 6Br minus plus 10OH minus. I combine the H plus and the OH minus to initially get 10H2O. But I already have 2 H2O on the reactant side, so I cancel that H2O, and that leaves me with 8 H2O on my product side. So my overall reaction is 2CrOH3 plus 10OH minus plus 3Br2 goes to 8 H2O plus 2CrO42 minus plus 6 Br minus. So that's balancing that in basic solution. All right. And now we're looking at H plus and H2O2 go and Fe to give 2 Fe3 plus and H2O in basic solution. All right, let's take a look at this. So my two half reactions are 2H plus H2O2 goes to 2H2O, and 2Fe2 plus goes to 2Fe3 plus. And looking at that, I see that there are some numbers out front. So I was curious. If I balance for hydrogen, and I have 2H plus from the H plus, I have 2 H's from the H2O2, and it gives me 4 H's on the product side. I also have the same number of ions on both sides. So awesome, that's done. Now, iron's done, H is, actually the H is done there too. The O's are okay, because there's nothing out of place there. So we need to look at the charge, and the charge, not okay. So 2H plus H2O2 goes to 2H2O. I need to add 2 electrons to the reactant side. So 2H plus 2 electrons plus H2O2 goes to 2H2O. With my irons, I have 2 Fe2 plus goes to 2 Fe3 plus 2 electrons. 2 electrons in both of them, so I can just add and simplify. I get 2H plus H2O2 plus 2 Fe2 plus goes to 2 H2O plus 2 Fe3 plus. And that is the reaction in acidic solution. However, this is basic solution, so we add 2 OH minus to both sides of this reaction. That gives me 2H plus 2 OH minus plus H2O2 plus 2 Fe2 plus goes to 2 H2O plus 2 Fe3 plus 2 OH minus. Combining the H plus and OH minus on the reactant side, I get 2 waters. But I already have 2 waters on the product side. And so that means that I have H2O2 plus 2 Fe2 plus goes to 2 Fe3 plus 2 OH minus. Sweetness. Which, of course, if you look at the reaction that they gave you, all you had to do was change it from H plus to OH minus. And that was exactly what we did. Okay? Last one. MnO4 minus plus SO32 minus goes to MnO2 plus SO42 minus in both acidic and basic solutions. Okay, so we have our MnO4 minus going to MnO2. We have SO32 plus 2 minus going to SO42 minus. Mn and S are okay. On our MnO4 going to MnO2, I'm deficient of oxygen, so I have MnO4 minus goes to MnO2 plus 2H2O. On the sulfur, I have SO32 minus plus H2O going to SO42 minus. So that way I have 4 oxygens on both sides. Now I need to balance for hydrogen using H plus. So I get 4H plus MnO4 minus goes to MnO2 plus 2H2O. And SO32 minus plus H2O goes to SO42 minus plus 2H plus. I then balance for charge. 4H plus 3E minus plus MnO4 minus goes to MnO2 plus 2H2O. So again, on the product side, it's completely neutral. On the reactant side, I had 4 plus and 1 minus, that gives me a total of 3 plus, so I need 3 electrons to add to that to get that to go away. I then look at my SO3 2 minus plus H2O goes to SO4 2 minus plus 2H plus, and I need to add 2 electrons to cancel the H plus because the SO3 2 minus and the SO4 2 minus take care of each other. So that gives me SO3 2 minus plus H2O goes to SO4 2 minus plus 2H plus 2E minus. I have a 3 electron process for the MnO4, so I multiply that by 2. I have a 2 electron process for SO3 2 minus, so I multiply that by 3. That gives me 8H plus 6 electrons plus MnO4 minus goes to 2 MnO2 plus 4 H2O. And 3 SO3 2 minus plus 3 H2O goes to 3 SO4 2 minus plus 6 plus 6 E minus. The electrons cancel, and I notice that I have water on both reactant and product sides, so I cancel the one on the reactant side, and that leaves me with 1 water, which gives me 8H plus 3 SO3 2 minus plus 2 MnO4 minus goes to 2 MnO2 plus H2O plus 6H plus 3 SO4 2 minus. And that's my balancing in acidic solution. And actually, it failed to cancel some of those H pluses, so I should be left with 2 H plus. So that's 2 H plus 3 SO3 2 minus goes to 2 MnO4 minus, 2 H plus 3 SO3 2 minus plus 2 MnO4 minus goes to 2 MnO2 plus H2O plus 3 SO4 2 minus. Now, since I also want to do this in basic solution, I'm going to add 2 OH minus to both sides. Sorry, I hadn't actually done this. That leaves me with 2 H2O on the reactant side. I already have 1 H2O on the product side, so I cross out that one on the product side and leave it as 1 H2O on the reactant side, which leaves me with H2O plus 3 SO3 2 minus plus 2 MnO4 minus goes to 2 MnO2 plus 3 SO4 2 minus plus 2 OH minus. And that is our balancing in basic solution. And that should be everything. So go us. We managed to balance 1, 2, 3, 4, 5, 6, 7, 8 of them. Practice, 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 practice. Notice that I was, generally speaking, able to pick out what am I supposed to do next, what am I supposed to do, half reactions, make sure that we're balanced for everything except oxygen and hydrogen, then balance for oxygen using water, then balance for hydrogen using H+, then look at the charge, then make sure the charge is the same, and then add and simplify. And if I need to do the next step, I get rid of my H+ by adding OH-. So those are my overall steps. Those are things you should be able to do. And when we get to the point where they ask us, okay, who was, and actually, let me go back and talk about that for just a second, because I think I skipped it. We're going to go back, and I don't know that I ever did. Where was it? Oh, yeah. So we had this MnO4 minus plus C2O4 2 minus goes to Mn2 plus CO2. Let me find my notes on that, because I can't remember. My brain doesn't work that well. I'm getting old. And when we balanced this, we saw that we had gain electrons reduced on the Mn, so that's the one that was reduced, and I lost electrons on the carbon, so that's my lose electrons oxidized, sorry. And if we wanted to look at the oxidation numbers, my oxidation number for Mn on the beginning side, so I have O, which is 2 minus, there's a 1 minus charge, there are 4 of them, that gives me a -8 there. the Mn, since there's only one of them, it has to balance everything except the -1. That gives me a +7. And this is actually in the notes that I'm giving you guys. I just forgot to talk about it. And I look at my Mn on the product side, that's a 2+, so that's the oxidation number there. When we talk about the carbon and the oxygen, that side, I know that in C2O42-, it's a -2 total. My O4 times, or 4 times 2- gives me a total of -8. I want 2- to end with, so that means I have to be left with a +6 charge from the 2 carbons. Since there are 2 of them, that means it has to be a +3 for each carbon. Okay, so it's the +6 for the total and +3 for each one. When we go to the CO2, we have oxygen is -2. There are 2 of them. That's a -4. Since I need that to be a neutral, then that means my carbon has to be a +4 charge. Okay? Hopefully I didn't confuse you guys too much. Like I said, that's in the notes that I gave you. I just failed to talk about it. So that gives you your oxidation numbers and who was oxidized and who was reduced. Okay? So hopefully that takes you through, gets you through everything you need to know for that portion of what we're going to talk about with oxidation reduction reactions. Next time, we're going to be talking about some other topics that are related to redox reactions, i.e. how we can use them and the energy that either they are created or need to drive certain things, and how we make predictions and talk about those systems. So that's what we're going to talk about next time. I will see you then. I hope you guys are good. If you have any questions, comments, problems, please let me know, and I will do the best I can to answer your questions. Thanks, guys. Talk to you later.